These are the answers for AERO 310 Section 1 PM section. The matching answers are shown over here. You can stop this video and check those answers if you like. I'm going to spend some time talking about the word problems, and the first one asks us a Tsiolkovsky equation where we have an SLS NASA rocket delta V of 7.4 kilometers per second to reach the moon's gateway station from low Earth orbit. Has a velocity, exhaust velocity the rocket has of 4.5 kilometers per second. So the first question is, what is the smallest percent of rocket mass propellant that must be fuel to travel round trip to the moon and back? Well, round trip would mean 7.4 times 2, that's 14.8 kilometers per second would be what I needed. And delta V is 4.5, so Tsiolkovsky equation, I need to take the ratio of that delta V to VE. So 14.8 divided by 4.5, right, 4.5 is going to give me 3.29. And now I can either use my calculator or I can go into this chart and go to, here's 3, there's 3.5, so 3.29 is about there. I'll come up and I'm going to come over and look right at 25. My mass ratio is at 25. So 1 minus 1/25 is 1 minus 0.04 or 96%, 0.96. So the answer to number 1 is 96% or 0.96. All right, the second question is, what maximum dV is it possible to get if I have to have 90% of my rocket's total mass can be fuel? Okay. Well, this tells me that my mass propellant fraction has to be 0.9. So I can go right into this equation, and 0.9, if I subtract 1 from it, will give me minus 0.1 on the left-hand side. The minus signs will cancel, so I'll get 0.1 equals e to that exponent. Oh, and I know that this exponent I can get rid of that minus sign by putting this in the denominator. So e to that positive exponent will equal 10, 1 over 1/10. So 10 equals e to that positive exponent. I take the log of both sides, and that gives me the log to the base e of 10 equals delta V over VE. I know what VE is, so my delta V will be VE times the log of 10, natural log of 10. Natural log of 10 is 2.3. Exhaust velocity is 4.5 kilometers per second. So if you multiply that out, you'll get the answer to 2 is 10.36 kilometers per second. Okay. The last two, number 19, the Cal Poly RV is flying at 150 miles an hour, lift coefficient of 0.2, and an angle of attack of 2 degrees. And I say, okay, well, what's the stall speed? I'm asking, what's the stall speed if it stalls at a lift coefficient, max lift coefficient of 1.8 with an angle of attack of 18 degrees. So that will take us back to our basic equation for C sub L, and the basic equation is C sub L equals the wing loading over the dynamic pressure. And dynamic pressure is 1/2 density times the equivalent velocity squared. That's Q. So this is wing loading over Q. I know that C sub L is 0.2. I'm at 1G. And so I'm over here on the C sub L alpha curve. I'm right here at 0.2, and I have 2 degrees. And my equivalent velocity is 150 miles an hour. That's given. So I'm going to go from 0.2 over the maximum, slow down, I go to 1.8, and that's going to take me to 18 degrees. That's given. And I notice that that's a factor of 9. In other words, 9 times 0.2 is 1.8, and 9 times 2 degrees is 18 degrees. So my C sub L is going to increase by a factor of 9. Now the G's are going to stay at 1, my weight's going to stay at 1, the wing area is going to stay the same. So that factor of 9 has got to come from the denominator. Now my sea level density is a constant. That's going to stay the same. So the 9 has to come from a change in the equivalent velocity. Now 9's in the numerator. So I see to get a 9 in the numerator, I would have to reduce the equivalent velocity by thirds. So in other words, V equivalent over 3. If I put V equivalent over 3, that 3 will come out squared as 9, and that 9 will end up in the numerator. So there you have it. If I take my stall speed to be V equivalent over 3, that 3, when I square it, will come out in the denominator of the denominator, so it'll end up in the numerator and give me 9. So my CL max of 1.8 then will be 9 times if I fly at the stall speed, and the stall speed will be 1/3 of my 150. 1/3 of my 150 is going to be what? 1/3 of 150 is going to be 50 miles an hour. So that's the answer. Okay. Last problem is a NASA probe discovers a huge asteroid between Mars and Jupiter. It's 4 astronomical units from the Sun. What is the asteroid's orbital period in Earth years? Okay, we have a nice simple formula. We have a nice simple formula for that. If you remember from the Kepler's law of periods. So Kepler's law of periods tells us if we use distance in astronomical units and the period in Earth years, we can use this nice simple formula that the period squared in Earth years is the astronomical units cubed. Well, the astronomical units here is 4. 4 cubed is 4 squared is 16, so 4 cubed is 64, and that's equal to period squared in Earth years. Well, if the period squared is 64, then the period has to be 8, right? So the answer is 8 Earth years. And so if we go back, we can see that indeed the answer is 8 Earth years. And that's it. Good luck.